So, good day everybody, wherever you are in the world, and thank you very much for taking some time to join this Bruker webinar entitled Thousands of PFASs, No Standards, No Detection, No Security. We have two excellent speakers today. I'll introduce them both to you now in a moment, and we'll take questions after we've heard both of their presentations. Our first speaker is Mohammed Saidia. He's a PhD candidate at the University of Amsterdam and part of the ITN, or Innovative Training Network, of the PFAS 3 project to investigate the environmental occurrence and fate of new and unknown PFASs in the drinking water cycle, and to assess the role of the drinking water in human exposure. He is focusing on developing new analytical methods for emerging organic pollutants in the environment using advanced mass spectrometry methods and applying these methods for transport and fate studies. And our second speaker is Dr. Silda Botendijk. She has a PhD in pharmaceutical chemistry and has been working for Bruker now for more than 10 years as an application specialist for timsTOF instrumentation. Her speciality is screening and quantification applications for forensics, pesticides, and environmental analysis. Her latest focus is on the combination of ion mobility with high-resolution mass spectrometry to bring targeted and untargeted workflows to a new level and further enhance the quality of results using Bruker's new trapped ion mobility timsTOF instruments, the timsTOF Pro series. And with this, I'm going to hand this webinar over to Mohammed, who will talk to you about his presentation. So let me just change presenters. So Mohammed, you should be the presenter now.
Yes. Can you see my screen?
Yes.
Okay, thank you, Megan, and I'm thrilled.
Yes.
Yeah, I'm thrilled to speak with you in this webinar about PFAS, and I will start with the PFAS general definition. So, Mohammed, thank you so much. Okay, so I will start with a general overview about PFAS. We're starting with very famous research about from back 2011, where he defined a terminology and classification of PFAS, where he defined PFAS as a fluorinated aliphatic substance that contain one or more carbon atoms that substitute all hydrogen with the fluorine atom. And by this definition, it's covered a very wide range of PFASs. In his papers and the authors, they introduce really very nice classification for the PFAS. But with time, so we can see there is more PFASs that's included in the environment and in this industry. It's not covered by this definition. So we can see 2018, OECD, they introduced a list of around 5,000 PFASs with a case number, and those of them, some of them, it's not in the PAC list. We can see the cyclic PFASs, like for example, the cyclic one on the left with the case number. So those one, it has different properties than, or different structure than what's proposed by PAC. So in 2022, we have a definition came out by OECD, and this is a very wide definition where they defined fluorinated substance that contain at least one fully fluorinated methyl or methylene carbon atom, and the methylene should be connected to other things than chlorine, fluorine, bromine, and hydrogen. Or in an easy word, we can say a chemical structure that contain in their structure CF3 and CF2 that's not contained to any of those halogenated atoms. And this definition is very wide, and it's covered a very wide range of chemical. If we look to the PubChem, the very nice website, we can see it's really big. So this is a really nice paper where they defined by Wang 2021. They make the different, to see the difference between different definition. We can see the new definition PAC and the OECD. There is different PFASs it's included in the by this definition, but also there is a few one on the down. It's showing that it's really different PFASs. You can see cursor, so we can see like this structure, like there's a methylene group with connected to the hydrogen, so this is not included as a PFAS on the OECD definition, similar to the other one with the bromine, iodine, and the hydrogen. So by looking to the PubChem, we can see that use this definition. There is a very nice tool in PubChem introduced recently. They call it PFAS-3, and this PFAS-3 is very nice that you can extract all PFASs based on their definition or their properties or use even. So on OECD, we can see that PFAS definition cover around 6 million PFASs. So this number is updated daily. Actually, now if you try to open it, it will be above this number. And this 6 million is very big number, and it will be very challenging for the non-target part. We know like it's not all this 6 million are in use or in the environment now, but most of them it's registered and filtered clearly in this tool in the PubChem. So PFAS, let's produce in different ways. So the most common way, it's electrochemical fluorization and polymerization. So electrochemical fluorization, it's the old one, which has been used by 3M. So they start, like for example, PFOS, the legacy one. So they start with octane sulfone fluoride, and they put it together with hydrofluoric acid, HF, in the pool, and they apply electrolysis. And this is very aggressive process, and they produce a lot of byproducts. So this byproduct like branch PFASs and cyclic PFASs, for example. So like PFOS, the famous one, we have 70% yield of linear, while you can get around 30% as a branch PFASs. Similar situation for other PFASs, so you can get it. The mix between linear and branched and other homolog. But also on polymerization, there's a different technique. It's in use after people different industry than 3M, like DuPont and some industry in China and India. So they start with initially by bentyl fluoroethyl iodine, and they add tetrafluoroethyl to their structure. So in this type of process, so for example, if they are aiming to C8 carbon chain length, they can get linear chain always, they cannot get the branch, but at this time they can get byproduct by different homogeneous series. So if they are aiming to C8, they might get a byproduct C6 or might C10, different number of carbon chain. So for the PFASs, we know like now it's really a huge number of PFASs now out in the market, but they have a lot of application and use. So those application is very important application in our daily life and our society functioning. So for example, it's used widely in building, construction, and electronic and semiconductor. It's used very well on the aerospace, military, defense. It's very important in our life also for automobile, for first aid. It's used now, all people start talking about alternative energy. So PFAS is used also in lithium battery and fuel cell, and in different chemistry. For example, now many drugs are now introduced to it's been in the market, it's considered as PFAS because they have the CF3 in their structure. So drugs, a lot of pesticide, herbicides, so all of them is considered as a PFAS, and based on the new definition of PFAS. So the regulating PFAS is really complicated process, and it's very slow process. So if we look to the EU regulations, so for example, the EFSA, there is dramatic decrease within 10 years between 2008 to 2020. For example, PFOS before were firstly regulated by 1,000 and 10,000 nanogram kilogram body weight per week to the sum of 4 PFASs to be 4.4 nanogram per kilogram body weight per week. So this is really very dramatic decrease as correspond to the toxicity study and epidemiological study about those two compounds. But it's very limited to those. The new direction, new drink water direction, they introduce a wider range of PFASs. So they make guideline criteria for the safe drink water to be in the range, some of 20 PFAS should be below 100 nanogram per liter, but also they introduce other parameter where its total PFAS should be below 500 nanogram per liter. So the EU member, they should choose one of these two parameters to fulfill for the drink water directive. So even in the US, they introduce a drink water a lifetime health advisory for PFOS and PFOA, which is really surprising, with a picogram per liter, 4 and 20 picogram per liter for PFOS and PFOA. And those level is very low limit of detection. You need a method that I don't think anyone in the world, they have a method below 4 picogram per liter in their limit of detection. It's very challenging. And I heard last week that on 14 February, the EU, they will publish the proposal to prohibit all PFAS use and application of PFAS in all EU member states. So to try to control the EU as PFAS as a one class. We will get a lot of discussion about this point. So the source of PFAS in the environment, of course, it has a lot of application, though that means sources, it will be a lot of sources. So industry is one of the main sources where they produce PFAS, but even where they use it, landfill and activity of firefighting foam in military and in airports. This is one of the sources. For surface water, we have the wastewater as one of the main contamination for the surface water. Similar situation application on the agriculture, like sludge, sometimes used as fertilizer, even pesticide or herbicides. It's been used and it's considered now as PFASs. So PFAS, there is a nice study 2 years ago about contamination from the fluoropolymer facility, where you can see that the contamination is not limited to the point source of the emission. So we can see like around 50 kilometers away from the point source from the factory, there is a high detection of the PFOA and GNX that they have been used in this industry, and that correspond to the atmospheric transport for those compounds. And those it's showing, this study is showing like a very high contamination upstream and downstream in the river. This same situation has been investigated here in Netherlands, in Dordrecht, where they have the fluoropolymer facility, and they found upstream and downstream in the river also contaminated in high concentration of GNX, because they produce GNX high level there. Other study that I tested drink water in Netherlands. Here in this study, we tested 18 different locations in Netherlands. We tested water from different sources, surface water and groundwater, and investigate 56, only 56 of PFASs, including the short chain, C1, C2, and C3, to the longer chain precursor and carboxylic and sulfonic acid. We see strong significant difference between different sources, surface water and groundwater, a high level in the surface water, while there is a lower level in the groundwater. But if we look to the yellow bar that present the ultra short chain, it's mainly TFA, the short one, C2, and we can see there is no difference between groundwater and surface water. That indicates that this very polar compounds, they are already in our groundwater, and those samples in the groundwater, few of them is presented very old groundwater, around 200 years old, and deep 200 meters below the surface, and this is like showing that the ultra short chain, it's already there. Other point in this study, we investigate the treatment. We test before and after treatment, and we noticed that there is no removal, really remarkable removal in PFAS in their treatment, and most of the treatment are in surface water. The water is still above the safe level introduced by Netherlands in RVM. So the others work in a human, so we can say that a human exposure is already included in all the world. This is a study from UN project where they investigate human milk, and that targeted 44 countries, targeted 3 chemical, PFOS, PFOA, and hexasulfonic acid, and we can see PFOS, PFOA detected in 100% of all in all the sample, while hexasulfonate detected in 80%, and this study is showing that the PFAS concentration even it's correlated to the income in the country. So when you are living in high income country, so we are expected to have higher level of those three compounds in the human milk and even in the serum with respect to the human body. So the analytical part, initially it's people early in 2000, they start to investigate the legacy one, PFAS and PFOA. With time, people introduce more PFASs. They start to include carboxylic and sulfonic from C4, we can say, to C15, 16. With time, recently, they start to include more PFASs like fluoropolymer PFAS, the ether acid, and the carboxylic acid and ether sulfonic acid. But nowadays, most of people, they start look to PFAS as one group. So most of people, they start look to PFAS as all PFAS, as the total PFAS, which is a really challenging part from the analytical perspective. So the analytical type, mostly for PFAS in general, most people use the targeted analysis, where targeted analysis they need to use, it has been applied for liquid chromatography and even for gas chromatography. So there is available now around 150 standard available in the markets, and it's really difficult to get and it's very expensive. Some of them, the non-target, the next very common used also nowadays, it's the non-target and the suspect screening, and that's what we are doing today here we'll talk about. And it's need to work with non-target screening and suspect screening need high resolution instrument, and specifically to get good separation and get exact mass. There, the other technique, it's total oxidative precursor assay, TOPA as it's called, and this is very nice method. So we can take the sample or the extract of the sample, we oxidize the sample by using OH radical, and I've convert all precursor to the carboxylic acid. Then we measure carboxylic acid, and by use this technique, we can estimate the amount of the unknown precursor present in the sample. There is a lot of limitation in the sample, but it's high promising technique. And the other parameter like total fluorine, extractable organic fluorine, and adsorbable organic fluorine. So this is very nice tools also, and technique can be used for PFAS detection. We can see this plot like the total fluorine normally in each sample, it's divided to the organic fluorine and inorganic fluorine, which is dark blue here. And in the organic fluorine is included to the part which is non-extractable and part of extractable organic fluorine. So the extractable organic fluorine, even if we look to it, it will divide to the part of it, which is most of the time, it's a small part. It's a non-organic fluorine that be known because we use the standard that we do it, we have it, then we know that the organic fluorine, but a big portion of it, it's unknown organic fluorine, it's unidentified organic fluorine, and this portion normally, it can be reduced by use other technique like total TOP assay or even the non-target and suspect screening, which can cover this unknown part of the sample. So the suspect screening, we can see like we have the nice paper from Eva Cheminsky, 2014, where she defined the different confidence level of PFAS of the detection in the non-target screening. And we can start with the last level 5, where they started with exact mass, MS in the level 5. And then if we go to the level 4 by use the isotope and the adduct, we can introduce the formula, the tentative formula. Then we can go to the level 3 by use of the MS2 data, and we can set a tentative structure and tentative candidate for our we can say target compound or our non-target or compound that we are looking for. Then by use the data from MS2 and compare this data with the library spectra and diagnostic evidence, we can get to the level 2, then the level 1 that's need to have a standard and check the standard and the retention time and compare that to confirm the structure. So this process is a very long process and it's time consuming, and most of the time people report their chemical level 2 or level 3, but it has you can use a lot of tools to try to reduce the problems in the non-target screening, because it's a time-consuming process. So they use like mass defect or Kendrick mass. They use like fragment flagging process, where it can help to reduce the complexity and try to filter the data in a portion that we can go in less time to go from level 5 to level 1. And ion mobility also introduced different advantage way by use the value of CSS that Silke will talk about it today. And this is very good to use it in different way in filtering, but even also to increase the confidence level and save a lot of time in the process. So the last part that to conclude that PFAS in the market are increasing in the market environment, increasing number of using also. That's a lot of use and application of PFAS in our daily life, in our society as well. PFAS, the contamination is not limited to the emission point, so that's why we can see PFAS it's reported in Arctic and everywhere in the world. So there is an analytical challenge to determine high number of PFAS with increasing, specifically when you go to the total PFAS and general number of PFAS. So using the non-target screening and go to high confidence level, it's really time-consuming process, and it's a lot of computation process specifically for the data analysis. So last thing, I would like to introduce you to the podcast that we are preparing in our project. We call it PFASology, and this part we talk about PFAS from different angles, from the treatment, from analytical part, but even from the solution part and toxicity. And thank you for listening.
So thank you very much, Mohammed. As I said, now we'll take questions at the very end after we've heard from Silke. I think, Mohammed, you have to make Silke the presenter.
Yeah, I think now.
So.
Okay, so
Silke,
just give me a second for the presenter.
Excellent.
Okay, so I hope everyone can hear me. So thank you very much for the very nice overview over the PFAS. So I think we have learned already a lot about the structure, about the classification, about the properties, the use, and the origin was also covered. So now I want to focus on the PFAS analysis and of course on the challenges that we have. They were briefly mentioned also by Mohammed already, but I just want to list them again. So first of all, one challenge is the huge group of compounds that we have. So more than or around about 5,000 compounds and all the degradation products. Secondly, we have a lack of reference standard. We have just heard that 150 compounds are available, sometimes quite expensive, but we are also lacking molecular databases in spectral libraries, therefore.
Silke,
and
sorry,
another challenge is...
Sorry, you're not in presenter mode.
Switch your screen.
You have to
I'm
switch.
not in presenter mode. Oh, I'm okay. I have to switch screens. Yeah, okay. Let me see. Bildschirm. Kann ich das ändern? Hm? Ja, kannst du.
Switch screens.
On top.
It's on the top, I think, Silke.
Ist hier oben.
Perfect.
Sorry for that. Okay. Okay, so now it's maybe easier for you to follow. Okay, we are still with the challenges. So now we had a challenge as well with the screen. But coming back to the PFAS challenges, so also a problem. Ja. Kannst nicht ausschalten. Sorry for that. Okay, so I start again with the challenges then. So huge number, lack of reference standards, and low concentrations have to be detected, and also sometimes in very complex matrices, like for example sludge. Another point that is challenging is the separation characterization of the isomeric PFAS compounds. So you can see we have quite a lot of challenges. So let's see what Bruker offers, what kind of mass specs we offer for maybe tackling these challenges. So we have our nominal mass LC and GC instruments. We have ultra high resolution for LC analysis, but also for MALDI analysis. And we have the ultra high resolution combined with the ion mobility. And there we are already with the instrument of interest for today. So it's the timsTOF Pro 2. We are combining this with our ELUT UHPLC. And if you have good hardware and good data, you also need a good software to handle these data. And so this is our software Metaboscape. So we have these players here. We have the timsTOF Pro 2 and the Metaboscape software. And I want to add another player to the game, which is the VIP HESI source. So it's our new heated ion source, which helps even more to improve sensitivity for the PFAS. So before going into the data reviewing, I would like to introduce these three players a little bit more in detail. So let's start with the timsTOF Pro 2. So what does TIMS stand for? TIMS stands for Trapped Ion Mobility Spectrometry. So next to the already known information that we get from LC analysis, the retention time, the accurate mass, the fragment information, we have now another dimension, namely the mobility, and we get the information for the CCS values. So it's another property that helps us to increase the reliability of compound identification. So what is the principle of TIMS? Here you can see these sailing boats. They should represent the different ions with different three-dimensional structures. And we are in the TIMS device. So in the TIMS device, a nitrogen tailwind comes and pushes the ions into the device against a counteracting electrical field. So kind of pushing them up to the hill. So the ions are trapped and held stationary according to their ion mobility, depending on mass to charge ratio and the spatial shape. And by subsequently lowering these potential, we can now do a controlled release of these ions. And what is different to the drift tube that you might know already is that in our TIMS device, the ions with the lower mobility, so with bigger CCS values, elute first, since we have trapped them in that way. Okay, here's another schematic view for this. So we have our instrument here. So we have the LC up here. Here's the capillary. The ions reach into the TIMS device, into the entrance funnel, and the nitrogen gas will push them against the electrical field. So the first thing that will happen is that we accumulate the ions separated due to their mobility. And in the next step, we have an elution phase where we are lowering the potential and eluting them step by step. So you can see we get very nice signals here in the analyzer. And we have also a time focusing effect here, around about 50, so that when you now generate MS-MS spectra, you get very high quality MS-MS spectra. So now you might say, okay, but since you're having an elution phase, you might lose some ions. So we are aware of that. So that's why we have a dual TIMS analyzer, where we can do in parallel first the accumulation in the first analyzer, while in the second analyzer, we are already eluting bit by bit. And when this elution is done, then from the first analyzer, the potential will be stepped down completely, so that all ions will be transferred completely into the second analyzer, and then the cycle can start again. So we have almost a 100% duty cycle here. Since we have a new technique, we also have a new way of producing data-dependent MS-MS spectra. which is called PFAS, parallel accumulation and serial fragmentation. This allows us to have more than 10 precursors per cycle, and so we have a very high MS speed. So we have, this is possible due to a TIMS synchronized isolation. So after one ion is released out of the TIMS funnel, it will be directly, the isolation will be triggered and the fragmentation will be triggered as well. So another benefit of our TIMS instrument is that when you have trapped ion mobility, you can change or adjust the ion mobility resolution. This is an example of 3 trisaccharides. Structures are shown here. You can see they are only partially separated in our survey view. So that's an overview scan that we are doing. So if we now change the RAM time and the mobility range, we can change the slope here, and we can go to a detection mode which has a higher resolution compared to the survey view, and which leads to very accurate CCS values. So you can see they are almost separated, and we can even increase the resolution further, going to the ultimate resolution round about a resolution of 200, where you can very nicely separate these 3 saccharides. So let's summarize again what the benefits of the TIMS Pro are. So we have a nearly 100% duty cycle for high sensitivity. We have a very clean MS and MS spectra due to the filtering effect of the mobility, and so we get very reliable results. From the mobility, of course, we also get the CCS values, so the collisional cross-section values, as an additional criteria for compound identification. We have the possibility to adjust the resolving power, so the resolution of the mobility, and therefore we can go to very high mobility resolving power to separate isomers. And we have, of course, ultra-fast data MS up to 120 Hertz. And so we have a very high MS coverage. And last but not least, we have an orthogonal design, which you might have captured when we looked at the schematic. So the source is in an orthogonal source design, which helps with the robustness. So looking at the source, we can switch now from the timsTOF Pro to the VIP HESI source, which is our new heated electrospray source. So we have, the name stands for vacuum insulated probe heated electrospray. So we have a heated source and vacuum insulated, which is displayed in this picture. We have a high efficient ceramic heater, which you see around here, but we also have vacuum insulation. So the heat of this heater is only transferred to the solvent or the liquid right before it goes into the spray. So this is protection of the thermally labile compounds. So degradation is not seen too much. And another point is that we have an active exhaust here so that we reduce matrix effects and have less source contamination and memory effects. In addition, what the source also has is that you can, next to ESI, also use it as an ABCI source. So what does the source help? So the source helps with the sensitivity. So if we compare our new source with the regular Apollo source, this is an example where 237 pesticides were analyzed and 10 replicates were done, and you see the frequency over the signal to noise of the VIP source and the signal to noise of the Apollo source. And what you can see here is that the signal to noise is always higher for the VIP source, and in average we get a gain by a factor of 12, which leads to a sensitivity gain for most of the compounds of a factor 5 to 10 compared to the original source. So having this good hardware, now we want to look at the software, the MetaboScape software, which helps us to identify compounds. So we have a workflow from the raw data to compound identification. Of course, we start with our TIMS data, the LC-PASEF data that we load into the MetaboScape software. And the MetaboScape software has an algorithm that does an automatic mass and mobility calibration a feature extraction, so combining isotopes, adducts, and charge stages. Retention time alignment is done, and of course the MS information is imported automatically. Then we have a feature table, and this feature table can be now taken for annotation of compounds, for screening for compounds. So the first step would be that we use a target list for knowns or suspect compounds to assign to the different features compound names. If this has been done, the next step would be that we can do further identification of unknowns. At least we can assign some formula using the smart formula tool. What is also incorporated in Metaboscape are some tools to reduce complexity of the data files or the data sets that you have. You can either do statistics, for example, doing a principal component analysis or a t-test, or you can also filter, as already mentioned by Mohammed, with mass defect specific MS fragments, or you can use the Kendrick mass analysis. So let's have a look at the target list screening. So in the target list, what you normally have is you have a name and a sum formula resulting in an accurate mass that you want to use. Now, if you have standards, you can use experimental data such as retention time and CCS values, or even library spectra could be added. But since we have a lot of PFAS that do not have standards, we also have the option here to use theoretical structure information, the in-sheet structures, to predict in silico fragments and to also predict CCS values. If the screening has been done with the target list, I mentioned already that you can then identify unknowns with further tools. So the first step would be you can try to use spectral library approaches, even though we know for PFAS they are quite rare. But in the next step, you can, of course, calculate elemental compositions using our smart formula tool, and also the smart formula 3D takes the MS fragments into account. If you have then an elemental composition, you can send this elemental composition for structural candidate search to an online database search like ChemSpider and CAP and CABI will be searched then. And if you have a structural candidate, you can use the MetFrag tool that is incorporated into Metaboscape to do an in silico fragmentation and an MS spectral match. And you can go even further. If you can predict then metabolites to this structure and do an in silico fragmentation there. And this is done by the biotransformer tool. So to reduce the complexity, I already mentioned that you can do a PCA model, so a multivariate statistic, or if you want to compare two sample sets or two samples in univariate statistics, the t-plot, t-test, which is represented in the volcano plot. So let's have a look again at the challenges from the first slide or the second slide that I showed. So here are the challenges, and now we look at our toolbox that we have for Brook. So we have the PFAS source that I just introduced for improved sensitivity, and we have the TIMS device to add another dimension for the separation to get cleaner spectra and to maybe also separate isomers. We get the CCS as a conditional criteria for the compound identification, and of course we have a very high coverage of the MS fragments with a passive mode. Then we use our software Metaboscape that can do data reduction with the Kendrick mass analysis, and we can do the in silico fragmentation and the CCS prediction. We can use this as well to handle all these challenges here. So with that, I want to now switch to the data that we analyzed and processed. So this was an original and a spiked water sample that were provided by Mohammed and Samira from the University of Amsterdam. And it was, these two samples were analyzed with LC with a 20-minute gradient. And the MS analysis, of course, was done with our timsTOF Pro instrument and with the VIP HESI source in negative ion mode using the passive MS mode. Each sample was analyzed in triplicates to allow for statistical comparison. And of course, the data mining was done using Metaboscape. So going into Metaboscape, the 2 water samples were analyzed using the T-Rex4D algorithm. So a feature table was created, and the feature table can be also displayed in the survey view, where you see the M/Z value over the retention time. So you can see it's a very complex, or a lot of features have been annotated, more than 1,500 features. But nevertheless, for 95% of these features, MS-MS fragmentation was also found. So the passive mode really helped to get good information about all the different features. So first thing, if you recall what I mentioned before, is that we can do now a filtering. So the filtering will be done first by the Kendrick mass defect analysis, and this is a widely used method to facilitate the detection and identification of chemically related compounds based on exact mass. And the compounds, the PFAS, have all in common that they have a repeating unit, CF2, and given with a nominal mass of 50 and the exact mass of 49.9968. And this can be used for the exact Kendrick mass. So the observed mass will be multiplied by a nominal mass of this repeating unit divided by the exact mass of the repeating unit. And then the Kendrick mass defect will be calculated using this exact mass, but you use the nominal mass minus the exact Kendrick mass. So that it's easier to follow, we have 2 examples here. So the PFAS, the C8 compound, and the BFBS, the C4 compound. So we have the nominal Kendrick mass, and we have the exact Kendrick mass, which is calculated in this way. So you can see both of these have the same Kendrick mass defect. That means when you have a Kendrick mass plot, where you plot the Kendrick mass defect versus the M/Z, the homologous species will have the same Kendrick mass defect and will align horizontally here. So if we look at the 2 compounds we just calculated the Kendrick mass defect for, then you can see that out of the big blob of compounds, you will get these 2 compounds in a horizontal line, of course separated due to the different M/Z value. Another example would be the PFOA, which is also very common in C8, and the C9 compound. They will be also put in a horizontal line. And what you can see is if you use this Kendrick mass defect filtering for the repeating unit, then you will have a PFAS Kendrick mass defect range from minus 0.25 to plus 0.1. So this will be the region where we expect our PFAS components. If we go back to the picture that we had before, where we have the survey view, we now load everything in the Kendrick mass plot. And here it's not a filtered Kendrick mass plot, so you will see all the features. But if we now apply this a CF2 repeating unit as a filter, then you will see that we get all the other compounds up here, and the compounds of interest that have PFAS structure will be in this orange box here. And as an example, PFAS can be seen here. So we have now these 180 features that we can now use for further analysis, and to also check if the workflow that we are proposing as a standard-free workflow works well. So for the feasibility of the standard-free workflow, we evaluated 2 different types of target lists. So as mentioned before, the target list always includes a name and the molecular formula, or let's say the accurate mass. And then we choose one that has experimental data, such as the retention time, the CCS values, and the MS-MS data. And this was done for 25 compounds of the EPA 533 method. This is just an excerpt, but that you see we have the retention time and the CCS values. And we can use a second target list where we skip all the experimental data, but use the theoretical structure information from the in-sheet structures, so that we are able to predict in silico fragments and predict also the CCS values. So if we go now into the feature table for the experimental data, then you can see we have assigned to 19 features names here based on retention time and the CCS values that have been checked before with the standard. And if we now look at the results from the feature table for the one where we have only theoretical information, which can be seen here, you can see that we find exactly the same 19 compounds. So the approach seems to work with experimental data or with theoretical. That's why in the next step, we expanded this target list. Now skipping all the experimental information that we have, just using the structure information from the INCHI keys combined, or from the INCHI structures combined with the accurate mass, so that again the fragments can be predicted and the CCS values can be predicted. So if we look at the results here, it's again an excerpt of the feature table. You can see that 46 out of this 52 possible PFAS compounds have been annotated with quite a good CCS value accuracy. And I should mention here that we are still learning, so it's a CCS Predict Pro training model that with more and more PFAS CCS values fed can then lead to even better predicted values below 3%. And if we look at the group of FTS compounds, for example, again in the Kendrick mass plot, can very nicely be seen that 4, 6, 8, and 10 FTS align horizontally, and this one was picked as a new one, which now very easily can be seen in the Kendrick plot. Okay, so we have now used the filtering. We assigned already 46 compounds, but we still have some of these 118 features that haven't been annotated. So we now, for these annotated but filtered features, we want to look at what we can still do to analyze more. So what was done here is that we only wanted to look at statistically relevant or significant features. So that's why we used the t-test. So how to read the volcanoplot, which is a graphical display of the t-test results. So the black dots are common or are shared between the basic sample or the original sample and the spiked sample. And on the left-hand side here in this blue arrow in orange area, in this labeled in orange, you can see the features that are found in the spiked sample. And some of them are already annotated here, but there are also some that have not been annotated. So we want to concentrate on these unidentified compounds, and this is an example how to do this. We could do this for the others as well, but just an example for one right now. So in the first step, we can assign a sum formula based on accurate mass and isotope pattern. And we can submit then these structures to the compound crawler. We can, after that, do an in silico fragmentation to match that with the experimental measured MS-MS spectrum. And then we can also do a prediction of the CCS value to double check if the fragments and the CCS values really fit to the structure that was assigned. So in the first step, here you see the smart formula tool, where we get results based on the accurate mass and the isotope pattern fit. And the best hit is the C13HF2502 compound, but we will take also the second one since it's pretty close in, or it's still a good hit. We will take just both to use them for the compound crawler and see what kind of structural suggestions we get. So this is then fed into the compound crawler. We get 10 hits out of there, and these 10 hits now can be sent to the in silico fragmentation. And if we look at the in silico fragmentation, you will see that you get a scoring, you get the number of fragments that have been assigned, and the intensity coverage, so meaning how many fragments have been found or have been covered. So you can see these two first entries, they have different names, but they stand for the same compound. So if we look at the major fragment here, it's the 618 found here in this spectrum, and it's the loss of CO2, which matches quite nicely. And as the main fragment, the 118 is found, which is specific for a linear structure here. Now we can predict also for all these structures the CCS values. And if we do this, we can see that for the ones that, these are again the same entries just coming from PubChem and ChemSpider, but the same compound, we can see that with the predicted CCS value, we are below 2%, which allows us to really think that this is then the compound. So what was the marked feature? At first it was unidentified, but using this workflow, we identified it as the PFTR-DA. Okay, so now to conclude, after having seen all these steps, that we found a standard-free PFAS screening workflow with the ion trap mobility, which enables the detection of multiple PFAS compounds in these two tested samples. And here's the workflow listed again. So we have a multi-dimensional feature separation using the TIMS with PASEF. Then we can go into our Metaboscape software where we can use the Kendrick mass defect for filtering, especially for the PFAS signals. And then we can do a target list screening. Afterwards, we can check which features are of statistical interest, and then apply these tools like smartphone, compound crawler, library search, and so on to find the non-targeted PFAS. So this workflow shows then an excellent potential to push the limits for today's PFAS and future PFAS analysis actually to a higher level or to a new level. And coming back to our title, thousands of PFAS, no standards, no detection, no solution. We can cross out the no solution part and put but a promising standard-free workflow powered by Bruker's trapped ion mobility with the timsTOF Pro and the Metaboscape. And with that, I thank you for listening, and a special thanks goes to Mohammed, Samira, and Rick, and of course also to Andrea and Eva from Bruker. Okay.
So thank you, Silke, and for a very enlightening talk there, and also Mohammed, thank you very much to you for your excellent introduction. And so now we can open this up for questions. There is a chat box in the control panel, and you're very welcome to submit some questions there. We've had a few coming in, so let me start. Silke, the first question that comes in is it's about calibration of the system, and which calibrant do you use, and is it the same for mass calibrant and CCS calibration, or do you have to use different compounds? So maybe you can comment on how to calibrate a TIMS mass spectrometer.
Yes, of course. Okay, so the calibration of the MS of the mass is done still by our calibrant, the sodium formate that we are using, and we are using a combination solution to also calibrate the TIMS. Then we use the Agent tuning mix that can be combined into one solution, so that the CCS values can be then adapted to the tune mix masses, and this will be done for the instrument in the beginning of an experiment or data analysis run. And then in each and every data set, there will be a short segment where you also infuse this combined calibration solution, so that all the data sets can be recalibrated with this with this solution, including the clusters, the sodium clusters, and the tune mix masses.
Thank you very much, Silke. Mohammed, there's a question for you. The Drinking Water Directive has introduced drinking water quality standards for total PFAS. And how do you measure the total PFAS?
Yeah, thank you for the question. In our sample, we investigate only 56 PFASs. So we assume that the total is 56, but we know that not what will introduced by Drink Water Directive. So Drink Water Directive, they didn't clarify clearly how to measure total PFASs, but they promised to introduce the analytical method somewhere end of this year or maybe earlier. So
Lovely.
we expect this soon. Yeah.
And so the next question, I think it's to you, Silke. Which other building blocks could be used to calculate the Kendrick mass defect? Is this applicable to more heterogeneous families of compounds, e.g. pesticides?
So I think it's about the Kendrick mass defect analysis. So you can filter for different units. So for all the repeating units. So everything that has multiple repeating units. So mainly it's used actually for polymers, but for PFAS we have also this repeating unit. So whatever repeating unit you have, if you have a CH2O or a CH just in general, or CF2 like we have it with PFAS, can be used. But I think the beauty for the PFAS analysis is really that we have this repeating unit, and that helps us really to get rid, or not to get rid of standards, but to not be too sad that we don't have the standards. I hope that answers that. You can put in whatever you like actually as a repeat, as long as it's a repeating unit.
Sure, thank you very much. I think this looks to be another technical one, Silke. What are the differences in the preparation of liquid and solid samples for this instrument? Is there any difference in the detection range of the device between liquids and solids? I guess that could be maybe the first one. Mohammed, could you answer about the sample prep between liquids and solids? Or
yeah, the sample, this sample, it's water samples. So we extracted solid phase extraction, and we do it. Solid sample, I don't think we can put it in the instrument directly, so it should be extracted. So mostly like what the type of the solid sample is, it soil, sediment, could be fabric. So different extraction methods. I think that's dependent on what you are aiming for. Normally when we work for the non-target, we try to avoid do a lot of treatments. So less treatment, less sample prep, that's to ensure that all PFASs are all the chemical that we expect it will be end up in the final extract, and we will set up under challenge of the matrix effect. So it's something like should be considered in balance between do cleaning or extracting extra steps and could expect more losses.
thank you. And I think there's a second part, Silke, about the detection limit between liquid and solid samples. I guess they'd be pretty much the same, but could you comment?
Yeah, so I think it's really up to how the preparation is done. I mean, you need, if you want to do liquid chromatography, of course, you need a liquid sample. So you have to see if your solid samples can be transferred with the right solvent. And also the sample preparation sometimes for PFAS is an issue as well, what kind of tubes you're using. So you shouldn't use maybe glass vials. But in general, I think if the sample prep is good, then there shouldn't be a difference between the different sample states. So if it's liquid or solid in the beginning, but of course you have to have a liquid.
Yeah, but I can add in this instrument, because we have it here in our lab, so we test on the standard around 10 picogram, we can detect it very clearly. I think it's a very sensitive instrument on this. Yeah, the ion source is really a big improvement with the using of the heating step.
I think this next question will be interesting for both of you, actually. I think you both comment, maybe you first, Mohammed. What issues do you have with external PFAS contamination, for example, from eluents or from the LC setup, etc.? Is it a big issue for?
In my case, it's not a big issue because firstly, I did most of the work alone in the lab. So we made separated lab, so we don't have any contamination issue within the lab. And the instrument, and this instrument, we didn't get any issue. I think it's really good to cleaning. Most of the time, most of the instrument they have with PFOA. The only instrument we have it in our lab, we have an issue with PFOA. It takes long time to be solved. Yeah, but this instrument, we don't have any issue yet. Hope not yet, also in future.
Maybe I can also comment on this. So we have PFAS kit available now from Bruker, where we have a trapping column and where we have all the lines exchanged by peak tubings, so that the contamination, so with the trapping column, you shift that back so that everything that is in the solvents, maybe in your
mobile phase.
Yeah, in the solvents will not be transferred. So we have this Teflon-free tubings and we have the trapping column in front, so we can avoid this. And if you also want to avoid from sample prep, as I mentioned before, you should see that you do not use glass vials but polypropylene vials, for example.
Thank you both very much. And another question that's come in regarding Metaboscape. And do you think that Metaboscape workflow could handle a huge target list, in brackets, thousands of compounds for MSMS and CCS prediction?
Well, I haven't actually tried such a huge number, and I don't know what huge is. I mean, if we talk about PFAS, 5,000 would be maybe a huge number. I know that it can handle quite a lot, let's say like 200 or 500 maybe, so maybe 200, but yeah, so maybe my colleague, she's Andrea Kien is sitting next to me, so she has experiences with these.
No, not direct experience, but we have generated target lists from the human metabolite database. So therefore, I assume it's not an issue. But I also haven't tested it by myself. But I know about the existing of such big target lists, and therefore I think it should work.
Thank you. Right, well, unfortunately, we're over time a little bit, so apologies for that. But again, I want to thank all of you in the audience for joining us and taking your valuable time to join this very important subject matter. Obviously to Mohammed and to Silke for their excellent presentations. If you do have questions, then please reach out to your local Bruker colleague, and they will be able to pass it back to the factory here in Bremen, and we'll get answers to you. So thank you all again very much for joining, and wish you all a very enjoyable rest of the day. Thank you all. Bye-bye.
Thank you. Bye.